All right, so we have one more section to go through in this unit, and that's dealing with the stretching and compressing of materials. So we just looked at Hooke's law, which was about springs, right? We had negative K delta X for the restoring force, and that's for anything that's a spring that's, coiled up or whatever. You can compress it together, or you stretch it out. Great drawings, right? And those exert a restoring force, but that also happens really for any object that we might even consider rigid, and that's just what this section is about. It's real quick, really interesting application, but not something that's covered in the scope and sequence of the AP exam. So if I were to have like on the right side over here, I have like a metal clamp. If I were to pull on that metal bar, the atoms and the molecules that are inside have bonds with each other, and they act like springs. So we can actually take most solid materials, and we can say that they're connected with spring-like bonds inside the stuff. So if I were to pull hard on a steel rod, it will slightly stretch the bonds between the particles, thus making the rod longer. So you can actually pull on it, a piece of metal, and you will physically make it longer. Now, steel, to some extent, is elastic, but under normal forces, it experiences very, very, very small changes in dimension. We call this rigid. We call these objects as being rigid. So rigid means that it doesn't bend. It keeps its shape if it's rotating or if it's having forces act upon it. That's what rigid means. It keeps at its shapes. Rubber bands and other materials that some can be easily stretched, we call those as pliant. But really, we're saying that these two different types both kind of impact each other. Or all rigid objects to some extent are pliant as well. So for a rod, the spring constant, that K, depends on the cross-sectional area. How wide it is makes it difficult. It gives it a higher spring constant. And the length of the rod makes it easier to stretch it. And this one other variable here, this is Y. This is Young's modulus. And Young's modulus is a property of the material. So if it's steel or if it's some type of carbon or some type of other metal alloy, Young's modulus is like its coefficient of friction, except it's how rigid that object is. So, here's a quick check. Bars A and B are attached to the wall, and they're pulled with equal forces, but one of them is stretched half as far as the other one, which has the larger value of Young's modulus. Well, A is going to have the larger value. It stretches more, but it has half the cross-sectional area, or a quarter of the cross-sectional area, because it's the radius is a half. So it has a larger Young's modulus. Again, not really an important concept, but we're just kind of talking about how it applies to rigid objects. So any object has the ability to be bent, essentially, and how much it can get bent or what type of force it can undergo is determined by the object itself, the Young's modulus, and how far you stretch it and how much force you can apply over an area. So we call this stress. Stress is a force exerted over an area. And then we also have strain, and strain is the ratio of the change in the length to the original length. So when you pull on something to make it longer, whether it's a rubber band or whether it's something like a steel rod, that's exerting strain. So when people make buildings, that's having strain put on, even if it's steel columns, by having all this mass either above it or below it pulling on it, produces strain on the building. And you have to be able to calculate how much strain it can take so that it doesn't collapse under the pressure or collapse under the force, because as we know from Hooke's law, as you increase the force, yes, there's this linear portion, but remember there's this exponential portion, and then there's the point that things break. So we need to make sure that we're calculating this stress and strain so the object doesn't break. So here's that that little graph again, a little bit different than the one that I had for Hooke's law. But as we stretch something, it tends to obey Hooke's law. But then we go beyond this elastic region, and as long as it's less than the elastic limit, the object will go back to its original condition. But once we hit the elastic limit, if we go beyond it, it will permanently deform it, and then there's some point which the object breaks. And this is all based on this concept of tensile strength. So tensile strength is how much force can be applied over a cross-sectional area before something breaks. One huge application of this is actual biology. So in your bones, you have different layers of your bones. The outside layer is your cortical bone or your compact bone. It's denser, and the inside layer is a little bit more spongier. And it does that so the outside is rigid. It has a very high tensile strength, and the inside is a little less rigid. So it can actually be more spongy. It can kind of compress a little bit without breaking. So that's getting into Young's modulus and stress and strain within your bones. Different things in your body have different Young's moduluses, means they break at different forces. So for example, when you're looking at things like your bones, there is some force that they can undergo over their cross-sectional area before they snap. And this is important for understanding things like collisions with people, so we can understand how much force they can have applied to them, especially in things like football. And then you can create like helmets and other materials that makes it safer for them. So all these they're just examples. They're engineering things, an interesting application of Hooke's law, but again, not something that's covered necessarily in the scope and sequence of AP Physics. But that does conclude our 5th unit. So where we're going next is we're going to do something completely different, and we're going to take a look at simple harmonic motion, which gets into mechanical waves and sound and how we quantify some of that. And then we'll take an introductory look into electrostatics and DC circuits. So again, something that's completely different, but there are some similarities that kind of come back as we deal with forces and conservation laws and stuff like that. And we'll be doing that in the next 2 units.